Hello, welcome. I'm recording this on a Saturday morning. Very alert, don't even worry about it. Today we're going to be looking at the second set of work for the Transition Metals workshops. So this is sort of workshop 2 material. The first question is about manganese, and the plan is to just rattle through that. Great to be with you again, hope you're doing well. Okay, so manganese 2 hexaaquo is pale pink, but this permanganate iron is an intense purple. That's interesting, isn't it? That's interesting. So manganese 2, using our group number of 7 and subtracting the oxidation state of 2, should give us 5 electrons. In an octahedral field splitting with weak field ligands, so delta is quite small. This ligand field splitting, this crystal field splitting is small. We can fill up 1, 2, 3, 4, 5 electrons. And this is an interesting configuration. The reason it's interesting is because of the really important selection rule. Delta S is equal to 0. So let's unpack that a little bit. Oh no, I've just drawn over it. Oh, what do I do? Do I do that? Oh no. Oh well, we'll just put this over here. Oh, hello. And I'll just put that over there. Oh, so professional. So professional. So this means that an electron cannot flip its spin. So you could imagine the action of light. Typical symbol for the action of light there, H nu. Promoting an electron. But there aren't many ways to do that. So if it promoted an electron from this orbital, it would have to flip the spin if it puts it into this other orbital up here. This violates the selection rule. So for this process, delta S is not equal to 0, and that means the transition is much weaker. That is why this octahedral manganese 2 system has a pale colour. What about the other one? So the group number 7 is the same, we're talking about the same metal, but the permanganate iron has an oxidation state of 7, plus 7. I think this is the only one of the first row transition metals to achieve its group number as an oxidation state. I think after that the effective nuclear charge just gets too big. But anyway, we're left behind with 0 d electrons. So if you're feeling super smug about putting all those in, you could draw out the scheme, but actually this is just vacant. There are no d electrons to talk of. And yet it has this beautiful purple colour. Why is that? Hang on, I'm going to not repeat the mistakes of the past. Yeah, there we go. Haven't drawn over anything at all. Oh, maybe it would be tetrahedral. Yeah, I think it would. I've drawn out the wrong scheme. So this permanganate ion has colour because of a different electronic transition. It's not because of movement of the d electrons, because there are no d electrons. What it is electrons from the ligand moving to the metal. So you could imagine a process something like this, where one electron on this oxide hops onto the metal, filling up one of these lower energy d orbitals over here. This is called ligand to metal charge transfer. It's often abbreviated LMCT, ligand metal charge transfer. And it's important that you've seen this for the studies you will do next year, but this isn't a big feature of the course. This is just one way of bringing back to your mind these ideas of selection rules for electronic transitions. Anyway, this is not forbidden. So you can satisfy the delta S is 0 rule. Oh, 0 not S, give that a big tick. And actually you can satisfy the other one, so I'm going to call it L, delta L. Distortions, what we call here is an asymmetric filling. An asymmetric filling of d bonds. So here's all about finding the number of d electrons. So chromium, say it's equal to 6. And in an oxidation state of 2, we're looking at 4 electrons. I wonder how those 4 electrons will up in optical field splitting. I'm going to suggest 1, 2, 3. And then with these weak field water ligands, it does pretty small, so promoting this electron will be favourable. And this will display a yarn-teller distortion. Why is that? It's because this electron here could instead be over here. So there's an asymmetry to the electron occupancy. So this could undergo a yarn-teller distortion. And it probably would, because actually these higher energy orbitals are more important for determining the yarn-teller distortion, for again reasons that will be discussed next year, to do with what's a sigma bond and what's a pi bond in the context of a metal system. Next example, iron 2. Iron is in my favourite of the D block groups, group 8, and we have 2 electrons, an oxidation state of 2 giving us 6 electrons. 6, not 2. That was my bad. How are these going to fill up? Well, 1, 2, 3, never have to think about those. And then again, we have a weak field system, so these water ligands don't do a very big band of delta. Next 2 are going to go up there. The last electron is 6 electrons. And in principle, this could undergo a yarn-teller distortion. So this electron here will down one here. Instead, go here, go up here. Not expect a big one. So these all stand here, not distortions. This is something. Copper. Copper is in iron. Currently putting together the science of copper. Anyway, group 9. Oxidation state of 2 gives you 7 electrons. Interesting. Let's see how it fills up. 1, 2, 3 weak field ligands. We've got 4, we've got 5, we have 6, we have 7. These are wrong. I'm looking at talk in Hull, and I've misidentified the group. This is all rubbish. Yeah. Thank you for taking this journey with me, but let's again. Copper is in group 11, as you will know. 2 electrons. I'm doing it again. An oxidation state of 2 leaves you with 9 electrons. Good, that's better. I feel happy for the first time in years. 1, 2, 3. Weak field ligands. 4, 5, 6, 7, 8, and we have 9. So it's actually quite similar to the that first case, the chromium. Here we have an electron that could go over here instead. So this will undergo a yarn-teller distortion. Actually, copper 2 complexes are famous for the yarn-teller distortion because there is no way of filling up 9 electrons without having an asymmetric distribution. That is just impossible. Yeah, so they're very pronounced. You will come across this in the Irving-Williams series in your further reading. So that's good. That's good. We're moving on. The next